Hello, welcome back. In this segment, I wanted to talk about a Boolean algebra problem given in this book written by Professor Bruce Barak from Harvard. It's a fascinating book talking about theoretical computer science. And one of the problems is given here. Suppose you need to design a Boolean circuit, right? Boolean circuit in this case means using and, or, and not. That should take a 4-bit binary number as an input and produce output bit 0 or 1. The condition is that if all the input bits are equal, the program should return 1, otherwise it should return 0. Okay, so how do we go about solving this problem? In fact, the author has already solved this problem, right, over here in this book. And the solution that was is making use of those gates or, and not. And if you count the number of gates, you see 3, 6, 9, 11 gates. Okay, so I asked myself, can we design another circuit which is from a functional point of view the same behavior but uses less number of gates, therefore it will be more fast and cheap. Okay, so I'm going to use program synthesis for that particular purpose, right? And I will show to you that indeed we can come up with an optimized version using program synthesis. So just to be clear, I'm not sure whether the author's intention here is to optimize the circuit. His idea appears to be just to explain how to solve this problem using Boolean algebra. So just to make it clear. Okay, what you're seeing here is the program synthesis syntax that we have been talking about for quite some time. I'm going to take 4 Boolean variables. So you can map Boolean variables to true or false. If the value is 1, you can imagine the Boolean value is true. 0 means false, okay, and vice versa. So the circuit we are allowing to use only and, or, not, and the program synthesizer should come up with a circuit using only these components that we are mentioning here, and that must follow the rules. The 16 combinations are outlined here. You know, if all of them are false, we expect the program to be true, and all of them to be true also, the program should return true. Okay, so other than that, everything else is just false. So we give all these constraints to the solver, and we let the solver explore the state space of the components we talked about. And it will take some time, but you will see soon that it is able to synthesize a circuit for us. As we can see here, the program synthesizer came up with an expression. Let me parse this expression for you. First of all, let's count the number of gates. Here, 1, 2, 3, 4, 5, 6, 7, 8. So we got a new circuit which is made of only 8 gates. So we saved 3 gates. That's good. Let's analyze why this is correct. Okay, let me first write it in regular notation. This is in a slightly different notation than we are used to. So this OR is applied to, let me first write the first component. It is A and B and C and D. Okay, that's the first part. And then we do an OR. OR is usually shown like this, with not here, right? Not is written like a number 7. Not of A or B or C or D. Okay, let's think about why this is correct. Let's assume the first case, right? All of them are 1 or all of them are true. So in that case, this will be true, right? Or equivalently 1. And this will be false because this is true, not you apply, this becomes false. So the program will return true in the end, which is correct. Okay, so that's good. What if the other case? Let's assume all of them are false. In this case, this will be false. This will be true because the not part will be applied to false, which becomes true. So the program will return true. That's good. Okay, so we solved the both cases. What about the mixed case? If A and A, B, C, D are different, then this will be for sure false. And if they are different, means there must be at least one place it's true. That means the whole expression with OR will become true and not is applied, therefore it becomes false. So you get a false here. Okay, so the program appears to be correct. We have proved it. Okay, and it's interesting that we only need how many gates did we set? 1, 2, 3, 3, 6, 7, 8 gates. So we solve this problem using 8 gates as opposed to 11 gates that were discussed on the book. Okay, that's basically it. Thank you very much for your attention.